right, welcome, and we're going to be going over the 2014 multiple choice questions. So we did these in class a little bit. We're going to go over the second half, which is 18 through 42. Only the questions from 2021. So the last 3 units have been taken out. That's why there's problems missing. It's kind of spotty, stuff put everywhere because anything from electrostatics, waves, and circuits has been taken out of the exam. So that's why. All right, so let's get started with number 18. We have a spacecraft of mass 4,000 kilograms, that's probably important, is traveling in a straight line in the positive direction. The graph shows data for a force. There's a force exerted, okay. And there's a graph, right? So first thing we need to do, you see a graph, let's do a quick analysis and be like, all right, what does the area give me? Well, the area gives me the y-axis times the x-axis, right? So that's going to be force times time. And force times time, that is the impulse. That is the change in momentum, okay? And the slope would give me the y over the x-axis, right? So force over time. Which, when I think about that, I don't really have a formula that uses that. So that's actually nothing. Nada. Zilch. All right? So that is just kind of using the graph. And now we can see what the question actually wants us to answer. The graph above shows data for the force during one interval. Which of the following is the best estimate of the net change in speed of the spacecraft from 0 to 4 seconds? So we are being asked to solve for delta V, change in speed. Now I know change in momentum, right? Change in momentum has change in speed inside of it because change in momentum is the same thing as mass times change in speed. So what I can do here is I can set this up and say, all right, this impulse momentum theorem, that the change in momentum is equal to the force times change in time. That's on your formula sheet. I know that there is mass times change in velocity right there. And that impulse right there comes from the area of my graph. And so really all I need to do now is get this change in speed alone. So that would be area over mass. Now I just need to know what the area is, right? These dots, as you can see, are going to show up in probably at least one problem on your multiple choice portion. Just use the dots to estimate whatever shape it looks like. Like this to me looks like it's a triangle, right? And then down here, this is 0. And then these are pretty flat across, so that would be like a rectangle, okay? If I use this triangle, this gives me an area of positive 1,000. Right? This would give me an area of negative 500. Excuse me. So the total area would be 1,000 minus 500. So positive 500. And the mass, we said earlier, the mass was 4,000 kilograms. Plug that in, you get positive 0.1. All right. Number 19. I hate this problem, but there's a couple things we can talk about to at least narrow it down, right? You have a rocket that is continuously firing its engines, so that right there tells me it's probably speeding up, right? As it accelerates away from Earth, for the first kilometer of its ascent, the mass of the fuel ejected is small compared to the mass of the rocket. Okay, it's kind of random. For this distance, so we got planet, right? We got rocket, ship. And it's firing away, okay? And it's speeding up. So the weird thing you should notice right away is all of these pieces that they list do not they're not the same. This is just for the rocket, right? This one is for the system. And then this one is for the system. So the rocket's kinetic energy, well, as the rocket speeds up, it's going to get more kinetic energy. So I know the rocket's kinetic energy is increasing. That lets us know D is out. Now the rest of these can be explained a little better with the actual rubric. So I'm going to put that right here. The correct answer is A. Okay, and this one, the explanation, the gravitational potential energy is proportional to -1/r, resulting in an increase in potential energy as R increases. Which doesn't make sense to me. Because as R increases, that's going to get smaller. So I feel like their explanation, this is why I don't like this problem. The solutions give an answer I feel like is a mistake. But they say the answer is A. There's their explanation. It is what it is. Won't happen on any other one of these. Okay, so 19 might just be a wash. Number 20. A block 1 is attached to a spring that oscillates. Now, oscillating, remember, I know oscillating is kind of a weird word. If something oscillates, it goes back and forth. Right? So, a pendulum. A pendulum that swings back and forth. Back and forth. Back and forth. That's oscillating. A spring that's kind of bouncing up and down or bouncing left and right. It's oscillating. Okay, so we have block 1 is at a point of maximum displacement. And then another block gets put on top of it. So there was this spring. Okay, it was at its maximum displacement. And then all of a sudden down here at that same spot, another block, same exact block, got put on top of it. And the question is, how does this affect the period and the maximum kinetic energy? So oscillating makes me immediately go to my equation sheet. And we scroll down. So right here, in this area, I have my simple harmonic motion equations, right? This has to do with period, just period in general. This has to do with period of a spring, which we are using. And then this has to do with period of a pendulum. Remember, capital T represents period. So we have, let's get back to here. We need capital T of a spring, period of a spring. Now, what things affect period of a spring? Well, spring constant. Let's get, right, this is the spring constant. And M is the mass. So what actually changed when we dropped another block on top? Well, the mass got bigger. So if the mass increases, right, the thing in the numerator increases, that's going to make the period increase. So we know right away the period needs to increase. So A is out because it said the period is smaller. And then C said the period is smaller, so C is out. Now I need to figure out maximum kinetic energy. Well, remember, the kinetic energy that this thing has to use is the most energy it can get is the energy that it has from the spring, right? When the spring is all the way stretched out, and if this is its equilibrium position and this is where it's stretched all the way to, if it's all the way stretched out right there, this would be all potential spring energy, right? When it's coming back through the equilibrium position right here, and it's got this velocity going that way, now here it would be all kinetic. So when we talk about conservation of energy, all the spring energy when it's stretched out is then getting put into kinetic energy. So the most kinetic energy it has can only be the same amount as the most spring energy it has. So spring energy, 1/2 kx squared. Right? We just talked earlier, the spring constant doesn't change, so this is the same. And then the amount it's stretching, well, remember they said that it's at the same maximum displacement block 2 is placed on top. So what that tells me is that this is the same also. So nothing changed about the spring energy, so nothing is going to change with the maximum kinetic energy it has. So the answer would be D. It's the same kinetic energy with a bigger period. (22) Child slides from rest, down slides A and B. The slides are the same height, right? There's friction because there's a coefficient of friction. Which of the following compares the change in kinetic and the change in potential? Well, right away, same height tells me that the change in potential energies for both the slides is the same, right? Because it's going from the same gravitational potential energy of whatever height it's starting at down to the ground, 0. So I know these have to be the same. So I can go down here and look, and anything that doesn't say they're the same is going to get crossed off. So B is out, and D right there is out. And when I look at these, A has a shorter distance than B. And so when we're thinking about kinetic energies, we know because this is a longer distance, D, well, then friction, the force of friction, does more work on the child, because more work means that friction took away more energy. It had a longer length of the slide for friction to take energy away from the child. So, and if you want to think about that mathematically, remember the equation for work is force times distance. So because there's a longer distance for slide B, there's more work done by that friction force, which takes energy out of the child, right? So the kinetic energy of A is going to be greater than the kinetic energy of B. So that answer looks at C right there. All right. 22 through 24. Student is observing an object of unknown mass. That is, there's that oscillating word again. Remember, that's just something that's going back and forth. It's oscillating horizontally at the end of an ideal spring. The student measures the object's period of oscillation with a stopwatch. Okay. The student wishes to determine the spring constant of the spring using measurements of the period of oscillation. Which of the following piece of equipment would provide another measured quantity? So again, we're being asked about period of a spring. We're being talked to about spring constant, all that. So I'm going to take a look at my formula sheet and be like, all right, this right here is my formula for a period of a spring. So I'm going to go back to my thing. Period of a spring, 2 pi m over k. We are trying to figure out what is k, right? This period of the oscillation, that period gives us that capital T right there. So we have capital T, period, and we have period. We're trying to get spring constant. So the only other thing we need is a mass, right? So we need one of these things down here that's going to actually measure mass. So meter stick, definitely not. Okay, motion sensor, no, that measures motion, like velocity. balance, mass. Right? The balance is the old one of these guys that had like 2 plates and you put stuff on top of it, right? Kind of old school. I don't know why they have this on here, but it's in the more recent exams they would say scale or something like that. So that is a balance, but you put stuff on one side and then you try to balance it out with the other side of something with known mass. All right, so the answer is C. 23, using a number of measurements, the student determines the following. We get this table of values. What is the total energy of the system? Okay, so I have spring constant. That immediately makes me think use potential spring energy. And if I need to, on my formula sheet, right, potential spring energy, I'm looking for capital U with a S. There it is right there. 1/2 kx squared. So 1/2 kx squared. That would be 1/2. K is 85 newtons per meter. And the stretch length would be the same thing as the amplitude of oscillation. Amplitude being like the biggest amount it's going to displace. So that would be 0.3 meters squared. And even if you were confused about that, you would be looking for a distance here. You'd be looking for something that's measured in meters or centimeters or something, right? So that's our only length. So once I plug all that stuff in, I get an answer of B, 3.8 joules. While the object is continually oscillating, the student determines the maximum speed of the object during 2 oscillations. The first speed is 3.5, the second speed is 2.7. Which of the following could account for the decrease in the object's maximum kinetic energy? A is wrong because of this. Increase the maximum potential energy of the spring. That would be like the amount of energy is changing, but we know conservation of energy. If energy is getting transferred around, you always still have the same amount, right? So A is out. B, energy was transferred from the spring to the object, which decreased, same reasoning. We're not decreasing or increasing the maximum amount of energy in it. There's just being passed back and forth. As energy was transferred back and forth, a greater average share of the energy became potent. That doesn't make sense either. So D is the only answer. Okay, the object lost energy to its surroundings. That could be something like friction, or maybe thermal energy building up, or any, like maybe you're hearing it, so energy is going out to sound, right? Any number of environmental things could be taking energy away. 25. Crate is on a horizontal frictionless surface. Okay, that's good to know. A force of magnitude F is exerted on the crate at an angle theta to the horizontal. The surface exerts a normal force, Fn, on the crate. As the crate slides a distance d, it gains the amount of kinetic energy. While F is kept constant, the angle theta is now doubled, but still less than 90 degrees. Okay. How does the new normal force exerted on the crate compare to the old normal force? So when this is doubled. So basically, like, here's the original picture. The new picture would be something like this, where the force is going up more. And this is now double theta. Right? So what does that mean? Well, think about it this way. If here, the ground right underneath it, the ground has to support all the way to the block, right? On this one, you're only getting this little component of this upward force. And so that normal force, there's this thing's weight, mg. So then there's a normal force going up. Good Lord. Okay, so mg has to equal the normal force and that y component so that everything's balanced out, right? Well, if this now, when you double this angle, this normal force gets, or this y component gets a lot bigger, right? So this number stays the same. This number got bigger. So the normal force from the ground doesn't have to support as much weight of the box because now there's more of the box's weight getting supported by this upward pull. So the normal force from the ground is actually going to get smaller. Doesn't have to hold up as much weight because this is getting pulled up more. So the new normal force would be less than the old one. As the crate slides a distance d, how does the new gain in kinetic energy compare to the old one? Well, remember work. This is the work energy theorem. Work is equal to the change in energy, so the change in kinetic, which is equal to FD cosine theta. And if you don't remember that, that equation is right here. If I know there's some type of energy change happening from a force, then I can take a look at this equation and be able to compute it. Okay. So let me find my this right here. What happened? Well, theta got bigger, which means cosine theta, right? The amount of x component here, like originally there was this big x component, right? So there was a lot of parallel force to this thing's motion. When the angle gets bigger, the amount of x force gets smaller, right? So right here, as the angle gets bigger, this overall work gets smaller. So and then like when you think about 90 degrees all the way up, there is no x. So basically x at 0 is 1. Cosine of 0 is 1. And as it gets bigger and bigger, that 1 gets smaller, 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 till cosine of 90 degrees is 0. Right? So it goes from 1 to 0. So the higher up that angle gets, the smaller cosine theta number gets. So the new energy gain is less than the old one. 27. Block on a level surface is attached to one end of a spring right here. The other end of the spring is attached to a wall. There is friction, okay, between the block and the surface. A person displaces the block from its equilibrium position and releases it. Which of the following shows mechanical energy as a function of time for the system? So take a look here. We got two different systems. We got only the mechanical energy of the block, and then we have only the mechanical energy of the block and spring. So I guess not only, but so graph on the left is for just block. Graph on the right is for block and spring. So if we're thinking just block, the block can only have kinetic energy, right? Because the block's moving. The block can't have spring energy because that spring energy is in the spring. So the spring energy is inside of the energy graph on the right, where it's the block and the spring. All right, so we got to think about what's going on. As a spring is going back and forth, it's going from potential spring energy to kinetic energy. And then it's just going back and forth between those two energies, right? So when we think about kinetic energy, when it's all the way stretched out, the block stops for an instant, right? So it reaches a kinetic energy of 0. And then when it starts coming back, it speeds up, and then it's just this constant battle of like speeding up, slowing down, speeding up, slowing down, right? So the block with its kinetic energy is going to go up and down. So we know, knowing that, the kinetic energy doesn't stay the same the whole time because the kinetic energy has to do with speed, and it's not staying the same speed the whole time. So C is out. Okay, the rest of these are all the same. So now we got to look at the block and the spring. Well, I know the energy of the system, right? The block and spring together, that energy needs to stay conserved. It needs to stay constant, right? All they're doing is passing the same energies back and forth. So the total energy of the system would not be going up and down. So it wouldn't be A. Could be B or D. And so how we choose between these two now is we need to remember that there is friction here between our two surfaces. Friction is going to slowly take energy away from the system, right? Remember, if friction causes heat, it's going to slowly take away from like that total amount. So that would end up being D, because you see right there, there's that little decline in total energy. Okay. (31) The figure above shows the net force exerted on an object as a function of the position. So graph, right? I got a force position graph. So area gives me force times position. Or a force times a length, or whatever you want to call it. Okay, to me, that means a force times a length, or a force times a distance, or a position. That is work, which is change in energy. We were just talking about that in one of the previous problems. The slope gives me a force over a position. So a Newton, a unit of force divided by a unit of length, this would give me a spring constant. Newton over a meter, right? So let's see what it asks. The object starts from rest at position x equals 0, acquires speed of 3 meters per second. What is the mass of the object? So I see speed and mass. So I'm thinking, and then with this graph, with a force position graph, I can figure out energy, right? So I'm thinking energies. And kinetic energy has mass and, let's see, kinetic energy right here has mass and speed inside of it. So that's going to be my starting point. So I'm going to say, okay, the kinetic energy is equal to 1/2 mass velocity squared. The amount of kinetic energy it has is going to come from the area of this graph. So all of the energy that's put into this, right, we can determine by finding the area of the graph. And that's from 0 to 0.09 meters. So that's that whole thing right there. So this area, what is this? 3 times 0.09. I don't remember off the top of my head what that is. All right, so we would say the area here is equal to 1/2 mv squared. And we're being asked to solve for mass, so I'm going to rearrange these and get that variable all alone. What's going on with my pen? Okay, they told us the speed right there. They told us we can calculate the area. Okay, 0.09 times 3 times 1/2. 0.135. So our answer ends up being 0.03 kilograms, B. Okay. 32, two identical carts. So that's always important. When you see that word identical, That's like same mass, same size, same everything, okay? They're free to move along a frictionless track. Good. Cart X is moving at 2 meters per second, collides with and sticks to cart Y, which is initially at rest. Okay, which of the following graphs best shows the velocity of cart X before? So only cart X. Okay, so right away I know something is going and sticking together, so its mass is increasing, right? Conservation of momentum means if something's mass increases, its overall speed has to decrease, right? So I know it's not going to stay the same speed. So A is out. Okay, B slows down a little bit, which is good. C slows down a little bit, which is good. Right? D, after that collision, all of a sudden just stops. Not going to happen. So D's out. So it's between B and C. So the question is, how much does it slow down by? Well, conservation of momentum. All of the momentums initially need to equal all the momentums at the end. You have the momentum of cart X plus the momentum of cart Y initially equals momentum of cart X final plus momentum of cart Y final, right? Well, initially we know cart Y was at rest. So this one is gone. And then they stick together at the end. So this could be, what do we say? They're the same mass. Let's just call them M. So this is going M, V, initial. And then when they stick together, they double their mass. So this is 2M, final, V, final. So let's see what happens. M's can cancel. Right, and you see that V final is 1/2 the original velocity. Okay, if we just solve for V final right there. So I would want, if it started at 2, the resulting velocity should be 1. So our answer is C. You could work that out, or you could just remember, hey, if the mass doubled, the speed should be cut in half. Okay. A spaceship and its shuttle pod are traveling to the right in a straight line with speed v. As shown in the top figure, the mass of the pod is m. So this is little baby m. This is 6m. The pod is launched. Afterward, the pod is moving to the right with speed vp, and the spaceship is moving to the right with speed vf, where vf is greater than, I'm assuming that should say vp right there, but let's see. As shown in the bottom figure. Which of the following is true of the speed of the... Ooh, this is a center of mass problem. Okay. What is true about the speed of the center of mass compared to the original speed v? That's what it's basically asking. Okay. Now remember, there's no like meteor coming and hitting the spaceship. There's no external forces. So no. Why do we care about that? Because almost every center of mass problem has this setup. No external forces. So if there's no change to, like, there's no external forces acting on your system, then the center of mass just stays the exact same. It keeps doing what it was doing. Okay? So originally its center of mass was moving to the right at speed v. So even after they part, its center of mass is still just going to be moving to the right speed v. So our answer right there is D. It's still doing just what it was doing. 34, the diagram above shows a top view of a child of mass m on a circular platform of mass 5m that is rotating counterclockwise. Remember, counterclockwise is positive. Okay. Assume the platform rotates without friction. Which of the following describes an action by the child that will result in an increase in total angular momentum? Here's the deal. This is the important part. Total angular momentum of the child platform system. What do we know about momentum? Conservation of momentum says the sum of all your momentums before, and this is angular momentum, so capital L, has to equal the sum of all the angular momentums after. The child and the platform are all one thing. They're like one system. So they cannot change how much momentum they have. Remember, only an external force or an external torque can do that. So they can't. Right? Even if the kid could run a certain way or whatever, but the platform, the child moves toward the center of the platform. Think about conservation of angular momentum. Has to do with I and omega. That has to do with rotational mass or inertia, and this has to do with angular speed. Right? If the child moves toward the center, you are decreasing the rotational inertia. So this would get smaller, but that means that the platform would just speed up to make sure this stays constant. So, but it wouldn't change the overall amount of angular momentum here. So A is out. Child moves away. It's the same thing in the opposite direction. If the child moved away, that would increase the moment of inertia, or the rotational inertia, but then that would just decrease the angular momentum, and the total momentum would stay the same. Child moves along a circle. Nope. That would change the child's momentum, but then the disk's momentum would change in the opposite way to balance everything out. Okay, so the answer is D. And I just walked through all those with you, but you would just know, hey, I can't do that. So you would immediately search out the answer that says you can't. Okay. 35, train traveling east with a constant speed of VT. So V train. Two identical spheres, so identical, are rolling on the floor of a train car. In the frame of reference of the train, the spheres are moving directly toward each other. So that means somebody standing inside the train car would see the spheres rolling towards each other. What is the velocity of the center of mass of the spheres in the frame of reference of the train and a person standing at rest alongside the train? Well, imagine this. If I'm standing outside, I'm standing on the ground. So there's a person over here just kind of watching. Right? And they're watching that. They would just see the center of mass. Right? The center of mass for those spheres just stays right between the two spheres. Right? So the center of mass to them is just moving along with the train. So the person is going to see just the thing moving at the center of mass for the spheres moving at the same speed of the train. So VT to the east. And that actually cuts everything else out because everything else is not that answer. All right. Right? If somebody was standing inside the train, like maybe they were right here, well, they would be moving along with the train and they would just see that center of mass not moving at all. They would just see the spheres rolling towards each other. So that's why this answer is 0 as well, because if the person inside the train, they wouldn't see the center of mass moving. It'd just be standing there. Okay? 36. A satellite that is spinning a satellite that is a spinning cylinder has a initial rotational inertia I is 0, angular velocity omega 0. Solar panels unfold from the satellite and are extended outward. The satellite then has rotational inertia IF and angular velocity omega f. So here's the deal with this. Rotational inertia, or rotational mass, is proportional to the radius. Remember, the mass, like where the mass is, relevant to its axis of rotation. The further away the mass is from the axis, the bigger that the rotational inertia gets. It's harder to turn something when the mass is further away. Okay, so when they unfurl their solar panels, I goes up because the radius went up. All right, so that's one thing. So we know right away that when we're looking at this, that A right there needs to be bigger than it was before, because now I is bigger than the initial one. Right? So A has to be greater than 1, than the initial one. So can't be equal to 1. It's got to be greater than. So B is good, C is good, A says less than 1. Or D says that A is less than 1. So D is out. Okay. Now, what happens to angular velocity? Remember, angular momentum, something spinning, is conserved. So this right here, this quantity right here for L cannot change. This has to be constant. So what happens is you have this balancing act, is as one thing over on the right hand side goes up, the other thing's going to go down to balance it out. Right? So if I increased, omega has to spin slower so that that number doesn't change. Right? For example, if this was, let's say this number, we could calculate it and this number was 10. Well, originally we could say that this was 5, which would make omega have to be 2. But now omega has I, the rotational inertia has increased, right? Well, maybe now the rotational inertia is 10. Well, that means we have to decrease omega to 1 to make that work. So you kind of see how these things, if one goes up, the other goes down. And there's always this balancing act to make sure everything stays conserved. So if I increased, omega has to decrease. So that little constant in front of it right there would have to be smaller than it was originally. So it's got to be less than 1. So that's going to be, our answer is B. 39. A person holds a 4 kilogram block at position A, shown above. Let me get my little notes for this one, just because. So here's the deal. The person gently lowers the block from rest at position A, and they lower it down to here. Okay. The best way to approach this one is just looking at what's the change in energy. Okay. We just got to calculate it real quick. At position A, the spring isn't stretched out at all or anything. It's uncompressed. So there's 0 spring energy. And so all there is here is gravitational potential energy. Right? At position B, we've compressed the spring a little bit. And so at position B, now there's some spring energy, and there's this new gravitational potential energy. Okay? So what we have is, we just got to figure out these things. Right? Gravitational potential energy, it's 30 centimeters, so that's mgy. So that's 4 times 0.3 meters times 10. So that gives us 12. Okay. Over here, Now we have this new potential energy at 0.2 meters, right? So this new one is 8, right? MGY here, this one is 8. But there's a spring energy now because there's been some compression. And you got to think, it went from 0.3 to 0.2. So that little bit of compression, 1/2 k x squared. This x right here is how much something has been stretched or compressed. So that x is only 0.1. Right? So when we plug in k right there, and then you plug in 0.1 squared, and you chug that stuff into the calculator, we get that there's a 2.5 joule spring energy. Okay? But here's the deal. That means we have 10.5 joules of energy. Right? Originally, we had 12. So we've lost 1.5 somewhere along the way. I don't know how. I don't know why. But it is what it is. Looks like some force questions, I would assume. The stacks of boxes shown in the figure above are inside an elevator that is moving up. Probably important. The masses of the boxes are given in terms of mass M. Okay. How does the magnitude of the force exerted by the top box on the bottom box, so force of top on bottom, how does it compare with the magnitude of the force exerted by bottom on top? Right? Well, that right there sounds to me like a Newton's third law question. Right? Force top on bottom, how does it compare to force bottom on top? Right? If I push as hard on something, it's going to push back on me with the same amount. So I know those two magnitudes are always going to be equal because of Newton's third law. Okay. 41, assume the elevator is moving at a constant speed. What does that tell me? That tells me that the net force is 0. All the forces are balanced. And consider the bottom box in the stack that has 2 boxes of mass 2m. So we're being asked about this one. Okay, so the bottom box, let's see, it was looks like that. Okay, and we're being asked about this one. What would be the forces acting on it? Well, take a look here. We got the force of gravity pulling it down. All right? You have the floor pushing up on the box with a normal force. And then the Newton's third law example that we just had in the previous question, that top box is pushing down on the bottom box. And so we would have 2 forces going down and 1 force going up. See. And then 42, assume the elevator has a, now we're accelerating up. So this tells me that the net force in the y direction is mass times acceleration. What is the magnitude of the force exerted on the top box by the bottom box? So mass times it, good, I guessed right, because it's this box is a mass m over here, so that's our mass. We're just dealing with the top box. The top box has a force of the box pushing up on it, and then its force of gravity going down. So it only has 2 forces right there. Right? So it would look like this. Force of gravity. I know it's accelerating upwards, so this one's going to be bigger. whatever that is. Okay, so Newton's second law. First of all, here's how we can just really quickly do this. It can't be equal to the force. We're solving for this upward force. I don't know where that E just came from. We're solving for this upward force. That has to be bigger than mg so that it accelerates upward, right? So automatically I know can't be mg. Okay? If I did ma minus g, that would be less than mg, right? So C is out. And then here's what I look at. My net force has to be equal to ma. That means that's my net. That's when I add everything together. If the box is equal to ma, then I would have ma minus mg equals ma. That would be all weird, right? So that wouldn't work either. So I know it needs to be bigger. The only one here that's guaranteed to be bigger than mg is the one that is adding two things together. It's adding something to mg. So our answer could be D. Now if you wanted to solve this real quick using Newton's second law, I would know, oh hey, I'm going to continue this, over here. I'm going to be like, all right, well going up I have force of box. Going down I have the force of gravity, mg. And all that net force needs to be equal to ma. And again, I'm being asked to solve for force of box, so I just move that other piece over. I rearrange this a little bit. And you could factor that m out like they did. And we got our stuff. All right, so the answer is D. Whew! Bunch of problems. But that was, for the most part, most of an exam, and still we would have like 45 minutes left. So I will see you all later.